Welcome. We are continuing our discussion on generalized minimum residual method, which is one of the Krylov subspace methods as we discussed, which is applicable for any non-singular matrix. Earlier we have discussed a number of Krylov subspace methods, and one of them, which is a very first method called conjugate gradient, we have seen that it is only applicable for symmetric positive definite matrices. Now, we are trying to look into methods which are fast as well as applicable for any type of matrices, not specific to symmetric matrix or not specific to diagonal dominant matrix like that. So, this is generalized minimum residual method, which we said is applicable for any matrix and is a fast method. And one important thing with generalized minimum residual method, or GMRES we popularly call it, one important point with GMRES is that this is an oblique projection method. That means the spaces Km and Lm are not same. So, let us start the discussion on GMRES formulation, which we covered at the last session. I will quickly recap of the formulation part also before going into algorithm in this particular session. Any vector x in the affine space x 0 plus k m can be written as x is equal to x 0 plus v m y, where y is an m vector, y has m components, a vector in R m, and v m are the orthonormal basis vectors of Krylov subspace k m. This is the basic idea of Krylov subspace method, and up to this any method, any Krylov subspace method is same with Arnoldi's method or with a full orthogonal method, that we generate the basis vectors v m, orthogonal basis vectors v m of Krylov subspace, and say that the updated value of x will be the approximated value of x plus a vector in the Krylov subspace, or a linear combination of members of V m. Now, the GMRES statement looks into a functional j y, which is L2 norm of the residual b minus a x, and so if we start with any general value of x, we replace x is equal to x 0 plus v m y, what we obtained here, we can x 0 plus v m y, we can substitute it here, and with little further analysis we have seen it in last session that this L2 norm is same as beta E 1 minus h m bar y L2 norm, where h m bar is the Heisenberg matrix that we obtained from Arnoldi's modified Gram-Schmidt method, and beta is the magnitude of the initial residual. So, we can also write that beta is equal to mod of b minus a x 0, or maybe second norm of that. So, beta E 1 minus h m y. This is a functional j y, which is second norm of the L2 vectors. We get that j y has this particular value, and now the GMRES approximation tells that there is an unique vector x 0 plus k which will minimize j y, and that is the solution, exact solution x. So, if we can find out a vector x 0 plus k which minimizes j y, that will be the solution of b minus equation b minus a x. So, my final x will be x 0 plus k which minimizes this. Now, minimizing j y is equivalent to minimizing this particular function beta E 1 minus h m bar y's L2 norm. So, we have to find out a y which minimizes this particular norm, and then we multiply this y vector with v m y with the basis vectors of Krylov subspace v m, and this x m is the solution of the equation. So, solution of b minus of a x is equal to b is obtained, and this solution is nothing but this x m where this particular value of y m which comes from the minimization of beta e 1 minus h m bar y. That is GMRES statement or GMRES approximation for solving x is equal to b. So, one important point is that it is right, if we think of conjugate gradient or if we think of steepest descent method, it was minimizing a different functional, and that functional was j x is equal to x transpose x half of x transpose x minus x transpose b. Here it is and when it was minimizing that functional, we observed that the residual vector is orthogonal to the space L m, which is same as k m. Here it is minimizing a different functional. Therefore, the residual vector b minus x is not orthogonal to k m, rather it is orthogonal to another space L m, and if we try to relate it with the discussion we had in minimum residual method, not generalized minimum residual method, in one dimensional projection process when we discussed about minimum residual method, we have seen that the space on which residue vector is orthogonal is V, where V is the space of in which x is updated, and therefore, here we using the same discussion we write that L m is equal to A k m, where R is equal to b minus a x is orthogonal to L m. Residue vector is orthogonal to a space L m, and L m is equal to A k m, and what is k m? K m is a Krylov subspace. And the formulation takes us to the fact that we have to find out first Krylov subspace basis vectors V m, and then we have to find out an y m which minimizes this function beta e 1 minus h bar m y, and this is equivalent to minimizing the L2 norm of the residual. And with this y m, we multiply this y m with the basis vectors V of V, and we will get the solution. So, essentially solving A x is equal to b boils down to find out the minimizer of beta e 1 minus h bar m y L2 norm. So, instead of solving A x is equal to b, what we are trying to do? We are trying to find out a minimizer of beta e 1 minus h bar m y is L2 norm. So, now the minimizer is inexpensive to compute as it requires a solution of m plus 1 into m least square problems, and m is typically smaller. M is the maximum dimension of Krylov subspace, or the dimension of Krylov subspace up to which the solutions converge, and it is seen that m is typically smaller than the actual matrix size. So, it is solving a smaller number of least square equations than the actual number of equations, and therefore, the solutions become faster. If we look into the algorithm quickly, the GMRES algorithm, so what again if we go back once before coming into the algorithm, sorry for that what does it need? It needs computing of V m and it needs computing of y m. V m is computed exactly same as V m are the members of the Krylov subspace, basis of the Krylov subspace. So, V m is computed exactly same in similar way as we have done in full orthogonal method or Arnoldly modified Gram-Schmidt. And once we compute V m, then there is a next rather smaller step which is computing the minimizer of beta e 1 minus h bar m y. So, if we look into the algorithm, the first part it starts with an initial guess value x 0 and computes the initial residual, finds out the value of beta which is magnitude of the initial residual vector, and then the later steps is right you take V 1 as the unit vector along R 0 or the initial residual, and then multiply this with A and subtract, which is a new basis of Krylov subspace, but as you want to find an orthogonal basis vector, you take the new basis and consider the old basis which is V 1 and take their dot product, subtract the dot product multiply with the old basis from the new basis. So, you get a new orthogonal basis and get orthogonal basis vectors, and in that way you also calculate the Heisenberg matrix and do till the Heisenberg matrix gives a j plus 1 jth term 0. That means, all the independent vectors in Krylov subspace, all the independent orthogonal vectors for Krylov subspace are found out, or the entire basis of Krylov subspace is found out. Do up to this part of M, and this part is very same as full orthogonal method, or it uses Arnoldi modified Gram-Schmidt to compute Vm, and Vm are basis of Km. Km is same for all the cases, it is the Krylov subspace, which is same for any of the Krylov subspace method, full orthogonal method, Arnoldi, Cg, Km must be same. So, this computation of Vm is exactly same as other Krylov subspace based methods. And once you have finished this part, then this is what is specific in GMRES, is the minimizer of beta E1 minus h bar M2. So, here you are actually finding out minimizer of r minus b minus x L2 norm. This is a new part in GMRES, and once you find this minimizer, because it is a smaller matrix, solving least square equation is like solving normal equation, which is much simpler than solving the large x is equal to b. When you find do this, so you found all the m's, and then in that process you have generated the Heisenberg matrix elements. These elements will go for the Heisenberg matrix h bar m, and you find out the minimizer, and this is the GMRES algorithm. So, the algorithm has couple of parts. The first part is find out Vm, same as full orthogonal method. In that part you also compute h bar m or the Heisenberg matrix, and once you have the Heisenberg matrix, you find out the minimizer of beta E1 minus h bar m y, and go ahead with that y ym, which is the minimizer, multiply this with Vm, add with x0. So, you find out ym here, and then this ym you take here. Similarly, you have found out Vm here, and this Vm is put here, and and the Hm you found out here, this Hm is used in this particular step, and that gives you the GMRES solution. So, instead of solving an equation, large equation system, we are trying to find out minimizer of a smaller number of equation of a smaller function, or we are trying to find out small number of equations, least square equations. However, there are few implementation issues. First is that in GMRES it does not provide the approximate solution xm at each step, rather because xm is found out when we have found out ym, which minimizes the function. So, we like an iterative method where we are every time looking into the solution and checking whether the solution is satisfying the actual equation. Here we are not finding out xm explicitly till we find out the right ym, which minimizes j. So, there is a issue of convergence, because the numerical solution we find out is never the very exact solution. There are round of errors or numerical errors. In an iterative method, the numerical solution converges to the right solution. So, what should be the convergence criteria? Convergence criteria is something that the error is of the order of round of error, or error is very small. Now, if we do not find out xm at each step, it is difficult to find out the error. So, there is a problem here, because we are using an iterative method, but through that iterative method we are not finding out the solution, rather we are doing an iteration for finding out minimum value of a particular function. So, when should we stop? That is difficult to make a call, because again, like if we know xm, we can see that how xm is different than xm minus 1, and if the values are small, we will say that it has converged and I will stop. But if we do not know xm, we are looking only into ym. So, based on what value of ym can we stop? And this is a little involved question. However, there are simpler solution, like check the residual with the ym, you find out what is the value of b minus a xm, or what is the value of beta e minus h bar my, though it is the minimum value, what is the value. If the value is not changing much, that means you have already close to the minimal value. Or if you see residual R0, if this is very small, then you can also say that b minus x is almost 0, so we can stop. That can be one remedy. However, there can be another solution in the way we propose the least square, find out the equation of least square solution. We will discuss it later, that instead of looking into the value of residual at each step, we can probably directly find out where to stop. The other thing is that when we are solving this least square equation, m plus 1 into m equation of a Heisenberg matrix, h bar m is an Heisenberg matrix. So, instead if we can transform the Heisenberg matrix to a triangular form, Heisenberg matrix is that a triangular matrix plus one row below the diagonal, one subdiagonal row. Now, if we can transform the Heisenberg matrix to triangular form, it is much simpler to find out the solution of least square equations, and conversion of matrix is possible through plane rotation. So, we will apply a transformation, a rotational transformation on the Heisenberg matrix and convert it to a triangular matrix, upper triangular matrix, and we will see that the issue of finding out minima of beta e minus h bar m y will be much simple, because although it is a smaller number of equations which are solving in least square equation, still we are solving a kind of a matrix equation, kind of A transpose A x is equal to x transpose b, things like that. So, A transpose A x is equal to A transpose b equation like that, which is a least square equation. So, there is some computational cost involved here, but now if we can make it much simpler, or by doing some transformation on the Heisenberg matrix, so that we come up with a upper triangular matrix, the computations will be further simpler, and this also will tell us, give us a very good nice way to decide that what is the value of xm directly, so that we can stop the calculations once xm has converged to the right solution. A common technique to solve least square problem is to convert the Heisenberg matrix into upper triangular form, and that is done by a rotation. So, here a rotation matrix capital omega I is defined as, it is a diagonal matrix with only a block of Ci Si minus Si Ci, which are the cosine and sine of the angles, which are calculated based on the I plus 1 ith term of Heisenberg matrix, if we are looking into the ith row only, or if we are trying to take the subdiagonal term from the ith row only, we will look into these values, the Heisenberg matrix I plus 1 ith term, and of the like this can come after several transformations. So, what is the value of the diagonal term of ith row after the transformation, based on which we can calculate S and C, which is basically C is equal to cos theta, S is equal to sin theta for plane rotation, plane rotational transformation, and therefore, C square plus S square is equal to 1. So, if m steps are performed, then sigma will, if their h bar m has m plus 1 into m plus 1 dimension, sigma m I will also have m plus 1 into m plus 1 dimension. So, how does it work? We will see on a take a 5 by 5 Heisenberg matrix and look into the example. This is an example which is directly copied from Yusuf Sir's book. So, we will see how this matrix can help us in finding out the triangular form. For example, we take a Heisenberg matrix which has basically 6 rows and the last term is H65, but this is m plus 1 into m plus 1. So, m is equal to 5. We take this Heisenberg matrix for m is equal to 5, and the corresponding beta G matrix which has beta as the first component and remaining 0 is there. So, we are solving basically beta E 1 minus, so G 0 is this is basically beta E 1 minus, we are trying to find out the minimal of beta E 1 minus h bar m y. So, if because I have to find out minimum of beta E 1 minus h bar m y, if I do a transformation on h bar m, or if I multiply h bar m with sigma I, I should multiply h bar m with beta with also with sigma I, so that it carries the meaning. So, entire thing is being multiplied by the same vector. So, now sigma 1, the pre-multiplier we for first row is C 1 minus S 1 C 1, and this will, our target is to give a triangular form here. So, triangular form will be a form like this. So, we have to keep on eliminating these vectors. So, by multiplying with sigma 1, our goal is that h 21 will be eliminated from h bar 5, and of course, g bar 0 after this multiplication will not be beta e 1, rather it will change from e 1, something else will come here. So, this is the pre-multiplier matrix according to the formula given in the last slide. So, when we multiply omega 1 with h bar 5, h 21 is deleted. So, this term is deleted and there is a minus s 1 beta which comes here. Now, we calculate S 2 C 2 and S 2 to take away h 32 term, and when we multiply this, this like from here we can see the 32 term, this has been cancelled out, and there are further more components in G bar 5. So, once we do this multiplications with h 2 h 3, like we take h bar 1 h bar 5 and then multiply omega 1 into omega 2 into omega 3 into omega 4 into omega 5. So, with each multiplication with omega 1 we cancel out this, with omega 2 cancel out this, omega 3 cancel out this, omega 4 you cancel out this, omega 5 you cancel out this. So, finally, you end up in a upper triangular matrix, and the G bar 1 is G 1 or the G matrix is converted into a 6, all the terms are populated instead of 0. So, it is a 6 non-zero terms in general come here. So, through a plane rotation we can take any h bar matrix of Heisenberg matrix and convert it to a upper triangular form with the last row having 0 only. The product of the matrices omega I is known as QM, omega m minus 1 to omega 1. QM when operated over vector beta 1 and matrix h bar m gives the following: R m bar is the upper triangular form with the lower row everything 0, is h m bar h m q m h bar m. G m bar is q m beta e 1 gamma 1 to gamma m plus 1. The R m is the upper triangular matrix obtained from R m bar by deleting the last row, since the last row is 0. So, if we look into the So, if we look into the last row of this is a 6 by 5 matrix. but the last row this is completely 0. So this will give me an 5 by 5 upper triangular form if I delete the last row. That is exactly what we are doing here. So, Rm is the upper triangular matrix obtained from Rm bar by deleting the last row, since the last row is 0. Similarly, Gm is the mth order vector deleting the last row of Gm bar. Now, beta E1 minus h bar my is equal to Qm beta E1 minus h bar my. Now, as Qm is a unitary matrix, multiplying with Qm will not change the norm, will not change the length, because its Qm is product of cos theta sin theta. So, Qm has a norm of 1. So, beta E1 can be seen as Qm into beta E1 minus h bar m's L2 norm is Qm into beta E1 minus h bar m's L2 norm. This is Gm bar minus R bar m y L2 norm. R bar m has the last row 0. So, we can write Gm minus R m y is L2 norm plus the last component of Gm, which is gamma m plus 1. Now, we are trying to find out minimum of this function, we are trying to find out its minima or minima of this particular function, and this is a function of y. A plus b, b is a function of y, b can change with y. When a plus b can be minimum? If b is a is fixed, b is a variable, if b is 0, a plus b is minimum. So, this function can have a minima when Gm minus R bar m's L2 norm is 0. The minima is, this is the minima of the summation, right. So, the variable part is 0 and the constant part is still there. So, gamma m plus 1 square is the minimal value of this particular functional, and so plane rotation it comes out very easily. And now, more interestingly, when for which y this is minima, the y for which Gm minus Rm y is L2 norm is 0. So, now we are in a matrix equation actually, this should be a 0 matrix, and Rm is a upper triangular matrix, Rm is an upper triangular matrix. So, the matrix equation is you only need n steps to solve the matrix equation. So, this will give you only need m steps, exactly m steps to find out the value of y, which will give the minimum value of this function. So, the minima will be obtained when the second term of the above expression is 0. Therefore, least square problem is converted into a m plus m into n matrix solver with Rm y is equal to Gm and Rm is upper triangular. So, we only need the backward swipe of Gauss elimination method to solve this equation. So, beta E1 minus h bar m square with Ym is equal to R inverse m Jm. This is what we are trying to find out. This minima is gamma m m plus 1's L2 norm of this, and when Ym is Rm inverse Jm. So, this will lead to a residual value b Rm is equal to b minus xm is equal to Vm plus 1 Qm transpose, and this is the minimum value Vm plus 1 Qm transpose gamma m plus 1 Em. Why Qm transpose? Because this is when calculating gamma m we have multiplied Qm with the beta vector, and the solution will be updated as x0 is equal to xm plus Vm Ym. Hence, Vm where Vm are orthonormal to basis of Krylov space obtained using Arnold's method. And this process must be stopped when the residual is small, and when the residual is small means finally this is gamma m plus 1 L2 norm, that is the residual. When this value is small enough, this process should be stopped. And solving as Rm is upper triangular, Rm Ym is equal to Gm needs Rm it has a dimension m into m, m steps only. So, now the GMRES algorithm can be solved in in order of m number of steps. So, if we take a large matrix and we find out the basis vectors of Krylov subspace converging base in which the solution will converge when gamma m is smaller enough. So, that gamma m plus 1, that is the value m, when gamma m plus 1 is smaller enough, the solution will converge, and that will need only m steps. So, it becomes a much faster method. And we also okay. So we also got a parameter to stop here, and that is when this value gamma m plus 1, when this value is small, solutions, this implies that solutions converged. So, we will quickly look into the convergence criteria of GMRES method. And n into n matrix GMRES converge at most in n steps, m cannot be more than n, and in m steps it must converge. Assume that A is diagonalizable matrix and let x is equal to x omega x in x lambda x inverse, where lambda is the eigenvalue matrix, all the diagonals of lambda has different eigenvalues of A, and epsilon to the power m is defined as a polynomial of lambda with different values of lambda 1, and maximum of that for the degree of polynomial will depend on for which this value is minimum. Then the residual norm achieved by mth step of GMRES satisfies that Rm2 residual norm at mth step is less than the condition number of the eigenvector matrix X into epsilon m R0 to the power 2, and therefore, the L2 norm of R0 is always greater than the L2 norm of the Rm. So, it should converge for any R0, and the convergence rate hence depends on the eigenvalue lambda of A, eigenvalue of A, and condition number of the eigenvectors. So, the method converges for any guess value x0. Convergence rate depends on condition value of the eigenvector matrix, not on the condition value of the matrix, rather condition number of the matrix, rather condition number of the eigenvector matrix and eigenvalues of A also. So, this is a very important method because this is applicable for any general type of matrices. Now, though this is an important method, this is a first method, in implementation wise it might be little complex if we compare with conjugate gradient, where if we look into the programming, we will look soon, the programming in conjugate gradient is much simple than the programming efforts for GMRES. Now, we will next few classes we will explore that if conjugate gradient type of methods can be extended for non-symmetric matrices, and we will get a algorithm called biconjugate gradient method. In the subsequent classes we will discuss on that. Thank you.